Day 19. So we're still going. We're on track today. We've managed to get this one done in a pretty reasonable time today. It wasn't a super difficult problem, but it was pretty fun nonetheless. It's sort of almost kind of it's like a pattern from one of the earlier days. I can't remember which day now, but you see when I start describing it, you may remember some people use this very particular approach to solve it, including myself, and a similar kind of approach ends up working out here to solve the problem. But yeah, it's not crazy difficult. But there's a little bit of kind of a mental leaps you need to make sure that you get the right answer in the end. So with that said, let's talk about this problem and then let's look at the code. So day 19, aplenty. So let's see. So yes, the elves on the Gear Island are very happy that with your help on the digging our trench from the last one, and they want to send you back to Desert Island, but there's even a hang glider here that someone stole. So you can return that. I wonder who stole that. So you reach the bottom and there's this relentless avalanche of machine parts coming down, forming a big heap. And the elves are trying to sort this into what parts are good or bad, or so they want to accept some parts and reject other parts, and they have a system in place for it. But basically, so the system has 4 criteria: extremely cool looking, musical, aerodynamic, and shiny. Xmas, which is great. And yeah, so they have these workflows in place that are basically like a series of checks that have to be done on each different part based on these criteria. And depending on that, you'll either arrive at a conclusion that the part is acceptable or that the part is not acceptable. So accepted or rejected are the two end states we're looking at. And so this is just a little bit about how the rule set works. But basically this is what our input is down here. So this is a rule set, and these are our parts that we're going to check. So each of the XMAS properties are property of that part. So each line of this represents one part, and those are all the properties of it. So what we're told that this is, so if you look at this, you can basically model this as like a graph. So there's all these keys which are unique, and inside each key there's a set of instructions that you have to run. So you are supposed to run the instructions sequentially. If the check that's in the instruction is a valid check, then you stop going through that and you take the value that's there and you move to that point in the next workflow, and then you check through it in the same fashion. And eventually, as you go through that entire thing, you'll either end up somewhere where it's an A or an OR for the return value, and that'll be it then. So you don't go any further, and at that point you'll know for that part, if you've gone through the whole map and reached an A, that part is an acceptable part, or if you reach an OR, then it's a rejected part. And yeah, that's about it really. So what they want you to do is they want you to iterate through all of our parts and try and determine if they are each acceptable or rejected, and at the end then you basically just have to sum up a bunch of values at the end to get what your answer should be. So you sum each of these values per one and then sum them all together in total. So basically just flatten the whole thing down and sum all the values together and that of the accepted ones, and that'll give you your answer. So straight away, there's kind of a couple of things that jump out. There's going to be a good bit of parsing involved in this, which can sometimes be a pain, especially when you have these sort of conditions. If you're using a language like Ruby that lets you do like text evaluation to code to execute, then this is going to be super handy because you can use exactly this text as it appears in your actual code, which is useful. But aside from that, we're effectively just traversing a tree pretty much, and we'll reach an end state of the tree if we traverse it correctly, which will be either accepted or rejected. So it's not super complicated. And also the fact that they tell you that these are they execute in order and they stop once you get a successful one. That also simplifies this too. So for the first part of this, there's no need to do any fancy, like really complicated nested loops or recursion or anything like that, because the first one you find that's successful will return, and that's it. So with all that said, let's have a look at the code and see how we wrote it. So yeah, so the first thing I'm doing, I'm creating an array for all my parts, an array for accepted, and an array for rejected. This is just to keep track. There's more for when I was debugging. I realized I've made a slight mistake, so I wanted to just store the entire list of all the accepteds and the entire list of all the rejecteds. Then I have a hash here for my workflows. So the workflows are going to be stored in a hash, and that's how I'm going to do my how I'm going to model my graph. And yeah, that's it for the setup. Then yeah, there's this workflow. It's just a toggle to let my file parsing logic tell it whether it's parsing a part or parsing a workflow definition. So the first, I'll just jump to the end here. So if we're parsing a part, it's much simpler than the other one. So I just get rid of the square brackets around it. I split the string by a comma, and then I split those strings by an equal sign and take the second value and cast it to an integer. And that gives me it's just an array of integers that represent the XMAS property of that part. So this parts array is a nested two-dimensional array where each entry is an array of XMAS for that part. That's just handy. I did it that way so I could use some splat operators down below, which is just a handy way of passing in an array as parameters into a function. So next thing then I'll go back to here where we do the workflow parsing. It's a little bit more complicated, but it's not crazy. So we're able to split this up. We're able to split out our so yeah, we're basically splitting on these squiggly brackets so that we can get to just where all the conditions are. We extract out the key, which is that first entry in the data. So we extract out this, and then we basically just want to extract each of these that are separated by a comma. And then we'll either have a check that we need to output and a destination to go to, or we'll just have a destination, in which case we don't have to do anything with the check. So that is what we're doing down here. So we get a check and a destination. Just because of the way this tuple assignment thing works in Ruby, that in the single case where all we have is just the destination, it'll actually be that value will actually be the check value because it'll be the first one in the array. The other one won't be used. So if the destination is nil, I know that's my case, so I'm just returning the check, which will say basically in my loop will just tell me go to the next point in the array or in the map. So then the second point, this is where we're able to use eval, which will just let us evaluate the string check, which is quite handy. So what this will do is, so this string check will literally have the character a XMAS or S in it, and then it'll check against a value. If I pass in all the values XMAS, then I'll have this thing that'll return if that evaluates to true, which for one of them, for the valid cases, it will evaluate to true. But obviously I don't know which one I'm going to be passing in because it's all dynamic in this case. So that's just, a simple way of doing it. Not the most clear thing, but I hope that explanation makes sense. Then what else are we doing? So then we parse it all out. So we now have our list of parts and we have our map of all of our workflows. So for each part, we need to effectively execute the workflow map on that part. So we're told that we always start at the workflow ID in, and then we go from there. So we'll start at in, and then while the next workflow doesn't equal a or, so that effectively means that we haven't hit one of these cases where the return value is an a or an or, we'll just keep doing this loop over and over again. So yeah, we'll increment the accepted count, we'll push into the accepted count the part that we currently have. If it's an A is what we get, and then we'll do the same for the rejected if we get an OR. And then at this point, we'll also just break out of the whole loop if we have either an A or an OR, because there's nowhere further to go with it. So, assuming that's not the case, so we're just on like the very first one. So if we have our next workflow is the very start, these won't evaluate. So we'll go down to here, and we need to basically pull out each of the steps that's inside that workflow. So ops here is basically an array of these little lambdas that I'm checking in here. So we need to execute each of those lambdas in order, and if they return something, then we need to stop executing, because it'll only return something it'll only return a positive non-nil value if there's a match there on the condition. If it doesn't match the condition, we keep going. And the thing is, what the trick is that you always get an exit, is that every single one of these checks always ends with a go-to move. And I think if you were to just trace all of those go-tos, they would always land at an A or an OR. So as long as you're evaluating that correctly, you'll always get to an answer, so you won't end up with an infinite loop. So yeah, we do that. We call this evaluation. So this is evaluating either of those lambdas, depending on which it is. The splat operator on the part here basically splats out those that part array into x and s parameters for the function, and it returns the next workflow. So the next workflow again could be an A or an OR. If it is, then we're done. If it's not an A or an OR, we go back into the loop again and check the next one, and we'll check the next one and check the next one, check the next one, until eventually we will reach an A or an OR, and then we can break out of the whole thing. And at that point, then we'll have an array of accepted values, an array of rejected values, and our answer will be we'll take all of our accepted values, we'll flatten them out, and then we'll sum them all together, and that gives us our answer. So we can run that on the sample code. Yeah, that runs very fast. That is the right answer. And then on the actual input, runs reasonably fast, and that is the correct answer. So yeah, that works pretty well. I wasn't, like, when I wrote this implementation, I thought I was kind of happy with this eval check thing and stuff, and then I thought to myself, they're definitely going to change this to make it more difficult or not as easy to use that parsing. So I think with a problem like this, it's not necessarily, I didn't expect that a problem like this, where the difficulty where they would extend it would be in the size of the values that you're expected to deal with. Spoiler alert, they do. But sometimes ones like this that have some sort of tricky parsing or stuff, they kind of just change the parsing to make it even trickier, or if you can come up with some clever way of doing it, sometimes that's how it works. In this case, not so much. But yeah, so if you're able to do that parsing, that will help you, but you have to be a little bit creative. And then you also have to try and apply that to where they've changed it. So let's have a look then at what they want us to do for the second part. So second part, the text is quite small, which is always a bad sign, because that means they're not giving us very much prompt, and they're just giving us a very clear thing to do. So what they say is the sorting process still isn't fast enough, and they've come up with a plan rather than go through all of them to see, maybe they can try and figure out what combinations will give you the best results, or what combinations will be accepted or rejected. So you want to try and figure out what are all of the, how many distinct possibilities will be accepted. So there's a lot of possibilities. So this big number here is 4,000 by 4,000 by 4,000 by 4,000. Sorry, you're also told that the numbers range from 1 to 4,000. And yeah, so that's a lot of numbers. So this is the way you get that answer. You arrive at that is the combination of any X, any M, any A, and any S will be the multiple of the ranges of those, which is 4,000 by 4,000 by 4,000 by 4,000, which gives you this god-awful large number. So immediately it should be obvious that you're not going to want to just test every combination and see which works, because you'll be there for a very long time executing that. So instead, what you're going to want to do is come up with some way that you don't have to execute every single number, but instead you can represent the state of any combination and then operate on that instead. So that's where the trick is. And in this case, the way I modeled that was each number, instead of it being, so each property, instead of it being a number, is actually a range or like an array of the values 1 to 4,000 for each case. And what you're going to be doing is, as you go through each loop, you're going to be taking those values and you're going to be basically chopping up the array. So you're going to chop up the array to the values that match the condition, and then the values that don't match the condition. And you're going to use that idea of having some values that match the condition and some values that don't match the condition. You're going to do a recursion and a nested thing across each of the checks you need to do. And at the end of it all, if you sort of combine all these values together, it will give you a total count of all the acceptable ones. That's a bit abstract. Let's look at some code and see if I can make that make a little bit more sense. But anyway, let's see. So, part 2. So a lot of this is the same. Up here, our parsing logic is more or less the same, except our lambdas now do slightly different things. So previously, the lambdas just returned what the next thing to check was, and and that was it. Yeah, that was all they did. It was just returned where the next place to check is, and all the state about whether we've got A's or R's was done just by counting up when we reach an A or an R. In this case, what we're going to be doing is slightly different. Instead of just counting that stuff, what we're going to be doing is we're going to be passing around these arrays that represent the state of what you have. So each array of state is the X, M, and A, and S values. And so our lambdas in here, they have now two things to do. One is they return us where the next place to go is. And the other thing they do is, depending on the rule checks that are in them, they will modify that state in some way. So the first case here, this is the case where it's just a straight go to something else. Doesn't do any modifications. So it just returns these arrays as they are. Down here, we want to return the destination, but we also want to return some modified states here. The reason we need to do this is that if you think about, if we always have a case like this. So if we look at the example, it's the easiest way to think through it. Say for so let's look at this one, the first case, the PX case here. So for the PX case, we pass in a state of XMAS, and into the first check, we're only looking at A's. So that's fine. So we know if we're only looking at A's, then in the range of values from 1 to 4,000, any value between 1 and 2005 will be a valid one. So that'll be a positive state. And then any value from 2006 to 4000 will be a negative value. So that will be like an unmatched state. And then we have a matched state and unmatched state. So what's slightly different about this problem compared to the last one is we can't just check the positive states and then break off, because there's also the negative state here. So we know that anytime we fail a check, we move to the next one. So in this example, if we're imagining we're looking at this whole range, for all the successful states, we'll make two new arrays. One that'll be the successful, and one that'll be the unsuccessful. The successful will have the values from 1 to 2005 in it, and the unsuccessful one will have the values from 2006 to 4000 in it. When we move to this one to do the next check, we'll give it the matching states, but we also need to go and check the second one because we had some failures. So we need to go and check that second one now. But the second one, we don't pass in the successful states, we pass in the failed states instead. And we keep doing that the whole way down each of these sets of rules until we get to the very end here. And the state that we pass in at the very end is just the combination of all of the unsuccessful states from the previous checks. I hope that makes sense. That's the intuition that I use to go through this mentally. But yeah, well, anyway, let's keep looking at the code and see. So what we're returning now is we're returning the place to go to next, and we're returning the successful state, and we're returning the unsuccessful state. Or sorry, I should say it's the matching state and the unmatching state. It's a bit messy in here, but I basically did some messing so that I could still just use that eval check. And then some of this, basically what this will do is, if it's an X we're looking at, it'll return the evaluated state, or it'll just return the original X. And so for any one check, only one of these will actually execute the filtering logic. The other one will just be the value as it was without being modified at all. And then for the negative state, so in Ruby, a select is just where it matches a case, and then a reject is just where it doesn't match the case. And so that gives us the opposites of it. So for example, if we were looking at if we had the array, if our X values were 1, 2, 3, then we'd have, and say if their check was X is greater than 2, this would evaluate and it would give me an array of 3, and then this would evaluate, give me an array of 1. But M, A, and S would all be the same regardless of what they were. If the input was, it would just be the same in the output. Okay, so that's our parsing logic. And yeah, so then to start this off, we're going to walk this whole path. So we're going to do this recursively because we need to do the nested looping stuff. I'll set up my initial state. So my initial state is just an array of 4 arrays of 1 to 4000 each, which represent the values, the possible values. And we start off at the in location. So we pass that in. If we've eventually gotten all the way down to the bottom, and A is where is the value we have, then we return. So this is basically just gives us the count, because we're dealing with arrays. The number of entries in that array will be effectively the number of possible X's, the number of possible M's, number so on and so forth. So we map that with the count, and then we do an inject to give us our total number of combinations possible. So that's the same thing as doing 4000 by 4000 by 4000 by 4000 for that case. But by the time we've gotten all the way down to this A, these arrays are going to be some set of values less than 4000 basically. And so multiplying all those together gives us the total number of the combinations that were possible to get us to that point. And we return that value. If we encounter an OR, we just return 0 because we don't need to worry about that. And then, yeah, so those are our exit conditions. So then the main loop inside this recursive function is the same as we saw before. We go through basically each workflow, we pull out the operation, except in this case, our operation returns three things. It returns the next one. It returns the matched states, the states that match the rule that we passed, that we checked, the states that don't match the rule that we checked. And so for this, then we recurse. So we call the same function again. We call it with the next one, and we call it the matches. We pass in the matches. So this is the positive case, but we're not done yet because we can't just do our positive cases. We said we also need to do our negative cases. So our negative cases, we just keep looping. Remember previously we broke here when we got a matching one, but in this case we have a whole range of matching ones, so we need to check each one. So we'll pass in so now we're going to update our overall state to equal the non-matched case, and then we're going to pass that in and just keep going in this loop until eventually we've checked all four of our, or however many operations we have, and yeah, that'll be it. By the time we've executed all these, we will have gotten down to all of the A's that were possible. We will have multiplied together all the counts of the state values, which gives us the total number of combinations. And then to accumulate them all, we sum all those together. And then that total at the end will give us our answer, which seems abstract, and it is, but it gives us our answer. So if we run 2 on the sample, that is the sample answer. It's a big number, and calculated kind of reasonably quick, not super fast. Now for my input, it is a good deal slower. So we're going to sit here and watch this for a couple of seconds. I think it takes just a little bit under 8 seconds, I think, to execute. There we go. Yeah, so just under 8 seconds. But that is the right answer. There's probably some optimization in this that I can do. This was literally the first time this spat out the right answer was the first time I ran it without an obvious like syntax error or something breaking in here, like a null check missing, which kind of surprised me. So I clicked the button and it just worked. So that's nice. But also I haven't really dug through it doing any optimizations or anything like that. So I'm sure I could optimize that down to get the runtime faster, but yeah, this works for what it is. Actually using arrays in here is probably a lot of what's slowing it down and doing this stuff up here. You could probably just use ranges instead to do this, but this check thing in here using the eval and just utilizing that for how succinct it made the code was handy. I'm sure there's some clever thing that I'm missing where I could do the same thing with a range and then it would probably be faster, because instead I'm just passing around. They're not big arrays, they're 4 arrays of 4,000 values max each that are being passed around, so it's not colossal, but it does have some overhead in doing all this, so sure, you can make it faster. Anyway, I think that is it for today. It was a fun one, not crazy difficult. If you kind of noticed the idea of, well, if I can split things into ranges and do the first and the last, that was a very similar approach to was used in, which problem was it? There was one of the problems earlier on this year where it was, can't remember, but anyway, there was ranges and splitting ranges was a big part of it. That was kind of hell, actually, that splitting ranges thing, but this is a hell of a lot easier, but the same concept applies and works. So you don't have to deal with big numbers, just deal with ranges, do some arithmetic, get your answers. Okay, so actually I should say that when I say do some arithmetic, I'm clearly not doing arithmetic. I created these arrays, but if you did do the arithmetic and built your logic a little bit better, you would be able to do it with the arithmetic and it would be extremely fast. Anyway, we're going to leave it there. Thanks for watching, folks. I will see you guys tomorrow.